We have proven up to theorem 103, and now we're on 104. And this is actually where we're probably going to end the portion of the lectures that's in this section, section 3.9. So this is where we'll end section 3.9. This is our last big result. Once you have transitivity and trichotomy, those two particular ones in place, you really can do anything with natural numbers and ordering. Those are the big ones. These other ones that you're seeing here, these are also in section 3.9. I'm going to leave these out of the course, but I did put some related presentation problems that you could pick related to minimum, which are interesting. These are things you will actually use probably later on, but we're not going to use them too much in this course, so I feel like you might just forget them if I just present them, and they're kind of complicated, especially while ordering. Maybe actually, now that I'm on this topic, let me just mention what it is. It's basically this. So every non-empty set of natural numbers has a minimum, has a smallest element. Smallest is defined here. The smallest element is one that is less than or equal to any other element. So this feature of the natural numbers, that every non-empty set has a minimum, this is called well ordering. And it turns out to actually be pretty much the same. It's equivalent to induction. So people use this sometimes rather than induction. So people use theorem 106 here rather than using theorem 94 often to prove things. And sometimes things are just cleaner when you use theorem 106. In fact, some people take theorem 106 as a sort of axiom that defines the natural numbers rather than the route we took where we define them to be the smallest inductive set. So you could take well ordering as your starting point in some way rather than induction. Okay, so for the last portion of this lecture, I just want to look at trichotomy. So this word trichotomy, it's like dichotomy, right? So a dichotomy refers to when you have two possible cases that could obtain, and it's one or the other and not both. That's a dichotomy, right? Two possibilities, one or the other and not both. Trichotomy is that, but for three. So given two natural numbers, there are three possible cases, and one of them holds and only one, so you cannot have more than one of them holding. And the different parts of this theorem are just precisely stating what is meant by either this or this or this, and only one of them holds. The first one is the or, which does not preclude that two could hold at the same time. So this is just saying either you have equality between the numbers, or you have an ordering, this one less than that, or that one less than this. So this is just saying at least one of them holds. Could be that multiple ones hold if all you know is number one. But then number two says, well, okay, it's not the first two both holding. Number three says it's not the first one and the third one both holding. And number four says you cannot have the second one and the third one both holding. So altogether, this is trichotomy. So let's state the part one of the trichotomy law. Assume n and m are natural numbers, then they've got to be related in some way. Either n, what order did I write this in? Yeah, either n, it seems I chose different orders here. How about I stick with this order? Either n equals m, or n is less than n, or m is less than n. At least one of these must be true. So this is not full trichotomy, this is just saying at least one of them must be true. Now, this will be by induction. and we're actually going to use previous results that themselves use induction, but this result also itself will use induction. So there are two choices of which variable to do induction on, and I'm going to fix m, so let's assume m is in natural numbers, and then I'll do induction on n. So we will prove that for all n is a natural number implies either n equals m, or n less than m, or m less than n, where we have this. Actually, here's where I needed the parentheses. Where we have m fixed here. For all n, at least one of these is true. Okay, so base case is going to be, we want to prove that either 0 equals m, or 0 less than m, or m less than 0. Right? That's what we want to prove. To prove an or, you just have to prove one of the things. So do you see anything here that we can just prove regardless of what m is? M was fixed at the beginning. We have basically no information about it. Is there anything here that's just true regardless of what m is? I would say not really. We don't necessarily know that 0 is less than m. I mean, maybe m is 0, then this one would be false. We do not necessarily know that m is less than 0. In fact, I think we know that this is false. And 0 equals m, well, that only happens when m actually is 0. But how about parenthesizing this or like this? I think this is actually something that's always true, right? So we have 0 less than or equal to m, i.e. 0 equals m or 0 less than m. And that's the proof of the base case. Do you see where I'm getting this, 0 less than or equal to m? I think it was one of our about 0. 0 is just always less than or equal to any given thing, no matter what it is. Any given natural number, no matter what it is. All right. By the way, it's things like that that make it important not to leave out these kinds of assumptions. So sometimes people get lazy and then they stop writing this is a natural number, like, duh, I'm using the letter m, that means it's a natural number. But there are actually things that you can use that do not become available to you until you make these kinds of assumptions. Like here we just used this. This requires that we're looking at a natural number. Otherwise it's just not available, right? So this line justified it. Okay, on to the induction step. So induction step. And now, always starts the same way. Suppose, and then whatever variable I'm doing induction on is a natural number. And suppose that the thing that I've written here that I'm trying to prove by induction is actually true, and then my goal will be to prove it, but with next n rather than n. So how about I just copy this? So now we're assuming an or. Okay, sounds like we're going to end up in a proof by cases. Right, we have an or. So our goal, just to keep that in mind, our goal is going to be to prove that either next n is m, or next n is less than m, or m is less than next n. And guess what? This is actually your homework. So from here, your homework is to finish this proof from here. So obviously you're doing a proof by cases, right? What you have is this big or, and then you're trying to prove this big or. Since you have an or, you're going to do a proof by cases. So So organize it as cases, separate paragraphs, numbered cases. Case 1, n equals m. Suppose n equals m, and then see if you can prove this or. If you have n equals m, then is there one of these that you think you can prove? Okay, then case 2, n less than m. Okay, now when you have n less than m, then is there one of these that you think you can prove? And maybe it's not just going to be one. Maybe in the case that n is less than m, you'll have to think about further possible cases. Maybe in one situation you end up proving one of these three, and in another sub-situation you end up proving another one of these three. Okay, so I think this one will be fun and not too challenging. And remember to pay attention to where you are. If you are, so you would be here working on this. So all of the later stuff is not available. The earlier stuff is available to use. I do want to look at in the lecture how to prove parts 2, 3, and 4. Those are not going to require any fancy additional induction or anything like that. They'll actually be pretty simple. So let's try part 2. So we can do all these by contradiction. So let me just kind of sketch things out instead of writing full paragraphs and stuff. So this is pretty simple. So part 2, suppose for the sake of contradiction that you do have m equals n and m less than n. So let's say you have m equals n and m less than n. And these are natural numbers. Where's the contradiction? So this is kind of fun. You might want to pause and try it. And remember that you can use anything that comes before up here. Okay, so here's what it would be. If m and n are the same thing, and this is true, then I can use axiom 2 or theorem 4, whatever you want to call it, to replace things by things they're equal to. So I can replace the m by something it's equal to, like n, and I get n less than n, right? But that contradicts the fact that that never happens for natural numbers. It's not allowed to happen. So there's a contradiction. These two cannot both be true. It'll be similar for this one. And then let's try this one. If m is less than n and n is less than m. So suppose n less than m and m less than n. So in my visual, n less than m, I think of n as sort of being to the left of m, and then here this is saying m is to the left of n. So it sounds like this is somehow contradicting the mental image of being able to line up the counting numbers in a linear sequence, kind of. But how to make that contradiction come out formally? Go ahead and pause the video and try it if you want to. Okay, and if I line things up like this, here's the answer. Then it's kind of staring you in the face, right? It's a transitivity thing. So go back here, theorem 100, part 1. If you have n is less than m and m is less than n, then it follows that n is less than n. But again, that's not supposed to ever happen. So there's our contradiction. Okay, so these parts are pretty easy. The hard work is in part 1, and that's the work that part of it you will do on your homework. And before I end the lecture, I just wanted to point out, now that we got this far, so now that we got, all the way through, all of these things are available to us, now we have exercises showing up like prove that 2 is less than 5 or that 4 is not equal to 7. And now we have tools to actually do these in a reasonable way. So, I don't know, remember this old exercise here, exercise 40? Back then, even this took effort. Now you know that this is actually proving that 0 is not equal to 1, right? And don't get misled. This one is about 1 is not equal to, and then this one is not a natural number. This is just some set that is not a natural number. But yeah, anyway, it took some effort to think about even these small situations. Now, can you imagine if you actually write out the definition of 4 and the definition of 7? It's going to be huge, right? Like 4 is next, 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 and then 7. It's just going to be a massive amount of writing to prove from scratch, to prove straight from, like if all you have is definition 90, the definition of 4 and 7, and definition 89, just the definition of next. Think about trying to prove think about with just those trying to prove that 4 is not equal to 7. It's not going to be a fun time, right? It's just so many cases to look through. But with all of the tools that we have now, it's actually easy. So I put that on the quiz. I put one like pretty short proof, and you can try to justify the different lines of that proof.